Good afternoon, everyone. We're going to go ahead and get started with our video. Information is going to be taken from Chapter 7, some of the information also from Chapter 8 and 9 when it comes to the bonding stuff. But let's go ahead and jump into it. Learning goal is I'll be able to relate the energy of a wave to its frequency and wavelength. Now, for the most part, that is actually going to be a very simple task for us to do. We just want to make sure that we understand. Oops, realize I made a little typo there. It's okay. We want to realize the role that each of these things plays and how it's going to help us to understand a little bit better the arrangement of the atom and how all these things are going to play together. Now, every 4th of July, and some people play with them a little bit more often, we go out and we observe fireworks and we see the blues and the reds and the yellows and we say, ah, this is so great. But what actually causes those colors that we see? Well, we have to consider a couple of things. One, why do we get colors? And two, why do different chemicals give us different colors? Because one of the big things you're going to notice is each of those different fireworks has a different metal or a different compound in it. Based on that compound and the metal that's there or whatever, we get a different color. Now, we have to consider a couple of different things. These three characteristics of waves or energy as it travels through space. One, the energy, messed up on that one. The wavelength, the frequency, and the speed at which it moves. Now, the third of the three is always going to be the same, okay? Always going to have the same speed, which we call c, which is, if you remember that from class today, 3.0 times 10 to the 8th, meters per second, or speed of light. SOL, speed of light. Now, when it comes to these characteristics, we want to look at a couple of different things. One is the wavelength. That's going to be the distance between two consecutive peaks or troughs in a wave. So if we're looking at an overall wave, which we'll see in the next couple slides, from peak to peak, that's a wavelength. Now, the frequency is the number of waves or cycles per second that pass a given point in space. So, depending on how long the wavelength is, would also give you an idea of how the frequency is going to be. And last but not least, speed of light, which is c, which I just told you. It says 2.9979 times 10 to the 8th, as most physicists will get on your back about 3.0 times 10 to the 8th meters per second. And this all works together in this nice little formula that we have here. Now, wavelength and frequency have an inverse relationship, meaning as the wavelength goes up or as the waves get longer, if this is my given point, as the wavelength gets longer, the frequency goes down. So that makes perfect sense. If I have a wave that's several miles long, it takes it a good amount of time to pass that point over and over. But if I have a very short wavelength, it's going to take a short time to pass that point. And this is what we're looking at here. If we're looking at each of these happening within 1 second, in this section that you see on the screen, here we go. If this is the number of cycles that are passing per second, we have four cycles for the first second. We shorten the wavelength and we actually get double the cycles in 1 second, so that'll be 8 hertz. And then we even make that smaller. We end up with 16 cycles per second, or 16 hertz. If you haven't guessed by now, our unit that we're going to use for our frequency is in hertz. Okay, so when we hear gigahertz, megahertz, all those different things, it's telling us how many cycles of energy are passing that point in a given second. Now, this all fits into what we would normally call electromagnetic radiation. So even the light that we see, notice that it has this very, very small section, but it's all energy that's traveling through space. From the shortest, which is going to be our gamma rays, shortest wavelength, highest energy, short, high energy, to our radio waves, which go all the way down here, which are going to be your long and low energy waves. Now, this little bitty section that we can see in here, of approximately 400 to 700 nanometers. That's the visible light that we're actually able to see every single day. And I asked the question in class today, what color was the shirt that I was wearing? One of the things that we're going to notice is, and this is more of a physics thing, but all these other wavelengths are absorbed, except for the one that usually they want you to see. And so they'll be dyed in such a way so that it reflects that color. Now, we're going to actually we're actually going to stop there for a moment, and we'll go into the next part in the next video. Take your time to read through. Make sure if you have any questions, direct them towards me tomorrow in class, and we'll handle it as quickly as possible. Have a great one.